Chapter 8.4, Compound Interest. Compound interest is interest computed on the original principal as well as on any accumulated interest. Recall from the previous section when we talked about simple interest accrues only on the principal. Compound interest allows your interest to earn interest. Okay, here are formulas for compound interest where A is the future value or the accumulated amount, P is the principal or present value, R is the rate of interest as a decimal, T is the time in years. So all of those we had on our previous formula for simple interests, but now we've added N, the number of compounding periods. The period of time between two interest payments is called a compounding period. When compound interest is paid once per year, N is 1, and we say the interest is compounded annually. This is the formula for when interest is compounded annually. Notice I really don't need this formula. It's simply this formula over here, and if I knew that it was annual compounding, I'd plug in a 1 for N and a 1 for N. Okay, so this is our main formula that we're going to refer to over and over, whether it's compounded annually or not. The book gives us these two formula. I only need this one. If compound interest is paid twice a year, N is 2, and we say the interest is compounded semi-annually. If the compound interest is paid 4 times a year, N is 4, and we say the interest is compounded quarterly. Okay, we can also have monthly or daily compounding. Of course, if it's monthly compounding, N would be 12. And if it's daily compounding, again, we talked about daily before. The banker's rule could use daily as N being 360 or N being 365 for just regular daily compounding. So pay attention to what our daily compounding period is going to be. Some banks also use continuous compounding. Think about this, not only every day or every hour that your interest gets paid to you and then begins earning interest, but every minute, every second, every fraction of a second. Okay, here's the formula for continuous compounding, where again, A is your future value or your accumulated amount, P is your present value, R is the rate of interest as a decimal, T is the time in years, and this E is a button on your calculator. So you may want to stop right now and find your calculator and find the E button. When you punch E on your calculator, you should get a non-ending decimal 2.71828 ... on and on and on. If you cannot find the E on your calculator and make it spit this number out for you, then you need to contact me and get some help with how to use your calculator. Okay, another thing you might need to know is, obviously, you'll need a formula sheet to work through these problems in Chapter 8, and you will be allowed to use that formula sheet on your exam. So you'll print a copy of your Chapter 8 formulas with you to take to the testing center when you're taking your exam, so you can use those doing your homework so you can get familiar with which formula goes with which kind of problem. Now, suppose we wanted to calculate the present value. In other words, let's say, I want to have $10,000 in 5 years. Well, what's the present value of that? What should I put in the bank right now, drawing this interest so that I have $10,000 in 5 years? Notice it's simply this formula right here, solved for P, right? Use your algebra and divide by this quantity that's being multiplied by P to get P by itself, and you have the formula for present value. The effective annual yield is telling us what the actual simple interest rate that produces the same amount of money at the end of 1 year as the compound interest stated. So we need to know the effective annual yield when we're comparing two or more possible sources for our investment, right? Sometimes we might have an investment that pays a little more interest, but another investment has more compounding periods. Obviously, the more times you compound money, the more money you make. Likewise, the higher your interest rate, the more money you make. So to determine our best option, we can do this effective annual yield. Basically, what this does is tell me what happens to every dollar in my account every year. All right, so let's look at some problems, how we might use these formula and our calculator to determine the accumulated value of an investment of $10,000 for 5 years at an interest rate of 5.5% if the money is compounded quarterly, and then do it again if it's compounded monthly. All right, as soon as I see this word compound, I leave my simple interest formulas behind. So compounding formula, and it doesn't say compounded continuously, so I know that I need this formula. First of all, the key to working all of these problems in Chapter 8 is going to be able to, first of all, pick the correct formula we need to use. Second of all, be able to know which values get plugged into which places in the formula. And third, be able to make our calculator tell us the correct answer. Okay, so here's the formula I need because it's compounded quarterly, and then I'm going to use it again for compounded monthly. Okay, and I have, let's change this color right quick, the accumulated value of an investment of $10,000. So this is my principal, what I'm going to start the investment with. 5 years, that's obviously my time, and it's already in years, so I'm good with that. The 5.5% is obviously my rate of interest, but I need to change it to a decimal, so I'm going to make that 0.055 to plug into my formula. And compounded quarterly means N is 4 because there are 4 quarters. 4 quarters in a year. Come on, choose my pen. Oh, okay, now choose my pen color. N. All right, so I'm going to plug these into the appropriate places in my formula. A is, now we already said that the 10,000 is my P. Okay, 1 plus the rate of interest is 0.055 over N, which is 4, all raised to the N times T. Now when I enter this in my calculator, if I do not put parentheses around this value, it's going to give me the wrong. If I just put 20, fine, I don't have to have parentheses around it, obviously. But if I'm putting 4 times 5, I have to have parentheses around that value. And now, all I do is plug that into my calculator. So I'm going to grab my calculator. Put 10,000, open a parenthesis, 1 plus 0.055 divided by 4, close my parenthesis, find my exponent, and by the way, you may be looking for what's called a caret, something that looks like this, or y to the x. Right, so look for these 2 keys depending on your calculator. Some of them may have something different. Contact me if you have trouble finding your exponent key. So mine has a caret, so I'm going to hit a caret and then open the parenthesis, 4 times 5, close the parenthesis, hit enter, and I get $13,140, and I get 0.66502. But obviously this is money, so it goes without saying that I would round this to the nearest cent, unless I'm told to round it to the nearest dollar or the nearest $10 or something. So again, pay attention to where the instructions are telling you to round. If there are no rounding instructions, then obviously round to the nearest cent. Okay, the next problem uses everything exactly the same, except I'm going to change in to 12, right? Because there are 12 months in a year. Now, I already have that in my calculator, and most of our calculators, unless we did not purchase the ones with the large screen, we can probably just go in right now and hit my second enter button, and it will enter this exact same information in my calculator, so I don't have to go in and do anything but go up and change the 4 to a 12. Alright, so I'm going to change 4 to 12 instead of re-entering everything. And I get, now, if I plugged in A equals 10,000, 1 plus 0.055 over 12 to the 12 times 5, and remember on the calculator I have to have parentheses around that, and when I hit enter I get 13,157.0370373. So again, I'm going to round this to the nearest cent for a final answer of $13,157.04. Notice with the extra compounding, that earned me an extra about $17. All right, what about this next one? How much money should be deposited today in an account that earns 6% compounded semi-annually so that it will accumulate to $10,000 in 3 years? Okay, so I want to know what I need if I want to have $10,000 in 3 years. That means I'm solving for the present value. So I'm going to use this formula. So let's go through and find all of our information. Okay, 0.06 is my R. Compounded semi-annually means N is 2. Okay, and accumulate to $10,000, this is my A. What do I want to have in the future? My future value, and T is 3, and it's already in years, so I don't have to worry about anything. So now I'm going to put 10,000 over 1 plus R is 0.06, N is 2, to the N times T, so 2 times 3. Again, if you don't just put 6 up there, you got to have parentheses around that. Plug that in my calculator. And I get that I should have $8,374, and I got 84256 0.7. Remember, when you're solving for present value, always round up. It does not matter what this next digit is telling you if you're solving for present value. If you don't round up, notice what this is saying. This is saying I need just a hair more than this amount and 84 cents, just a hair more. So I'm not quite going to reach my goal if I don't have just a hair more in. I always, when I'm solving for present value, round up. Okay, so I want to put in $8,374.85 just to make sure I meet that goal. In 1626, Peter Minuit convinced the Indians to sell him Manhattan Island for $24. If the Native Americans had put the $24 into a bank account paying compound interest at a 5% rate, how much would the interest have been worth in the year 2010? And it tells you that's 384 years, so I don't even have to go back and calculate that. If the interest were compounded monthly. All right, compounded. That means I'm looking to use the same formula because I want to know how much they're going to have in the future. All I have to do is pick the correct formula, plug my information into the correct spots, and know how my calculator works. Okay, so if he put the $24 in the bank, that's his principal. Paying compound interest at 5% rate, so that's his R. He, they, the Indians, right? How much would the investment have been worth? And here's my T, 384 years. Compounded monthly means N is 12. So I should have everything I need to plug in here and find out that P is 24, 1 plus 0.05 for the R, over N, which is 12, to the 12 times 384 years. And let's plug that in our calculator and see what we get. And I get a whopping 502,737,8919. Over $5 billion. Okay, from 24. That's the power of compounding, right? And it's because that's such a long time. But the point of that is, if you start saving when you're young, you're much more likely to wind up wealthy later in life. Right? The longer that you can save and invest, the better off you will be. All right, let's look at these last two and see what we have. An account has a nominal rate of 4.2%. Find the effective annual yield, rounded to the nearest tenth of a percent, with quarterly compounding, monthly compounding, and daily compounding. All right, so first of all, let's do that. It's telling me effective annual yield, so I have a formula for effective annual yield, right? It's y equals 1 plus r over n to the n minus 1. Okay, so let's do this first. We need to do it with quarterly, monthly, and daily. So here's quarterly. Let's do quarterly. Okay, let's go back and figure out our information again. The interest rate is 0.042. Notice the only thing I need here is the number of compounding periods and the interest rate. And on quarterly compounding, N is 4. On monthly compounding, N is 12. And on daily compounding, N is, it doesn't say use 360, so I'm going to use 365. So on quarterly, I have 1 plus 0.042 over 4 to the 4 minus 1. So let's plug that into our calculators. 1 plus 0.042 divided by 4 to the 4th power minus 1. And we get 0.0426661427. Okay, now it tells me to round this to the nearest 1/10 of a percent. So the first thing I got to do is change this decimal to a percent. Because it's a decimal and I'm going to a percent, I'll move in that direction. Okay, so this is 4.26661427, and if I'm rounding to the nearest 1/10 of a percent, here's my 10th position. The number to the right tells me to make that 4.3%. Now I'm going to do it for monthly. Okay, the only thing I have to change, the only thing I have to change is I'm going to change that 4 to 12. Instead of quarterly, I want monthly. So again, I can take advantage of my calculator and just hit a second enter, and I don't have to enter the entire equation again. And I can just go in and type over that 4 and make it a 12. Now be careful if you're adding extra digits, you might have to do an insert, but it's still quicker than retyping that whole equation. And this time I get 0.0428180072. And no, I don't have to keep all these digits, but I have to keep enough so that I can round to the 1/10 of a percent. Changing this to a percent gives me 4.2818. Okay, and if I'm going to change that to a 1/10 of a percent, they really should have asked us to change this to 100th of a percent. So we're going to go back and look at 100th of a percent also, so that we can come up with an answer to the last question. Now we want to do daily. Okay, daily is exactly the same, except I changed the 12 to 365, the number of days in a year. Same thing, I can hit second enter on my calculator and just go in and change the 12 to 365. And don't forget to do it in every place there is a 12. Okay, and we get 0.0428919589, which is, okay, I didn't put my percent sign in here where I needed it. At first I changed that to a percent, changed it to a percent, and then rounded to a 1/10 of a percent. So this is changing to a percent, 4.28919, etc. percent, and if I'm going to round to a 1/10 of a percent, right, then that is 4.3%. Okay, so that's the first part. Then it says, how does changing the compounding period affect the effective annual yield? Well, when they had us round that to the nearest 1/10 of a percent, that was a poor rounding place because now it looks like we're saying, oh, it doesn't affect it. Let's go back and round that to the nearest hundredth of a percent, right? Let's change this to a hundredth of a percent. Now I have tenths, hundredths. So I look to the number to the right. That makes this 4.27%. If I round this to the hundredths, right, the number to the right says leave the 8. So this is 4.28%. And if I round this to the hundredths place, the 9 indicates I should raise that to 4.29%. Now I can see what's happening. Changing the compounding period increases my effective annual yield, right? The more compounding periods I have, the higher my annual yield, my effective annual yield. All right, let's look at this last one. A bank offers a money market account paying 4.5% interest compounded semi-annually. Okay, so I know I'm using my compound formula. A competing bank offers a money market account paying 4.4% compounded daily. Which account is the better investment? Okay, that's another effective annual yield question. Right? I'm just going to calculate both of these in my effective annual yield formula. And here's my effective annual yield formula that I'm going to use. Except in the first one, I'm going to let R be 0.045 and N be 2. And in the second one, I'm going to let R be 0.044 and N be 365. All right, so let's plug in to my formula again. Y equals 1 plus 0.045 over 2 raised to the second power minus 1. I've already been using that formula, so I can just hit second enter on my calculator and change that 0.042 to 0.045 and then 2. Okay, make sure you don't make it 200, 002. So I get 0.045500625. And for the second one, I have y equals 1 plus 0.045, 044. Oh, 044 over 365 to the 365 minus 1. And let's see what we get. Change to 044. Go back to 365. And I get 0.044979 ... Okay, but I can already compare 045, 044. This one, 4.5% compounded semi-annually, is the better deal. It's going to give me 4.6% basically, and this one's going to give me 4.5%. Right? If I change this to a percent and round to the nearest 10th, changing it to a percent will get me 4.55%. This one would get me 4.49%, 4.497. I didn't really round that correctly. Rounding to the nearest 10th, because I wasn't rounding that, right? I was just truncating because I just needed 2 digits. So, okay, so 4.6% versus 4.5%. Alrighty. That ought to do us for this one. Let me know if you have any questions.